Once we take a spectrum of an astronomical object, besides disentangling these patterns, figuring out what the object is made out of, there's also a lot of useful information because of the Doppler effect.
The Doppler effect is the apparent change in wavelength of a wave depending on the motion of the source toward or away from an observer. Astronomers observe this effect with wavelengths of light, but we experience it with sound as well.
If you've ever stood there on a street corner and you've heard an ambulance go by, the first thing you hear is a very high-pitched noise, as it's, say, coming from your left and passing by you. And as it passes by you, what you hear are lower frequencies, a very low-pitched sound. So what is happening in that instance is, as the ambulance is coming toward you, the sound waves that are getting transmitted by the horn on the ambulance, the sound waves are compressed. As it goes away from you, those sound fronts, you could say, get stretched out. So it corresponds to a longer wavelength and a lower pitch. So you hear a lower sound. The same principle can be applied to light. If you have something coming towards you, you will see it, the spectrum get shifted, but towards shorter wavelengths, and those shorter wavelengths are mainly blue wavelengths. So it gets shifted, they say, toward the blue. If something, and this happens often in astronomy, if something is going away from you, it's going to get shifted toward longer wavelengths, and that's mostly toward the red.
These shifts are classified by the direction they move within the spectrum. Objects moving away from us exhibit shifts to the longer wavelengths. We call them redshifts. Objects moving toward us exhibit shifts to the shorter wavelengths and are called blue shifts.
I think the Doppler effect is one of the most important things in astronomy, because it enables you to say something about the radial motion of celestial objects, whether they move towards you or away from you. And the basic concept behind it, I believe, is very simple. It has to do with the fact that light is electromagnetic waves. Now, with a specific wavelength. And the color of the light corresponds to the wavelengths of these waves. So red light, for instance, has very long wavelengths, blue light has short wavelengths. Now the spectral lines, as I said, are in characteristic locations in the spectrum. That means they have exact characteristic wavelengths. So if a body is not in motion, I find these spectral lines at exact locations in the spectrum which corresponds to the laboratory wavelengths of those element spectral lines. Now, wavelengths of light, emitted light, can change if a body moves relative to me. For instance, the wavelengths become longer if the body moves away from me. And they become shorter if the radiating body comes towards me.
An object that is rotating exhibits yet another effect. As it spins, one part is moving toward the observer, while another part of that same object is moving away. A single spectral line will get both red shifted and blue shifted, which will broaden it, smearing it out in wavelength.
If that absorption line is smeared out, you know that that star must be rapidly spinning. You have a Doppler effect that shifts some of that light to the blue, some of that light to the red, and effectively smears out that absorption line. The Doppler effect also allows us to detect and identify binary stars. Two stars physically bound together by their mutual gravitation. What you see when you observe it, you might not see both objects. They're so far away that you can't resolve them. You see them as one object. But when you take a spectrum of that light, you see, no, there's actually two. You see a hydrogen line that's shifting back and forth. In fact, you see two hydrogen lines, one from each star, and they're moving back and forth in a very periodic fashion because of the Doppler effect. And from that, you can deduce that that's not a single object, it's actually two objects, a spectroscopic binary.
The Doppler effect is also helping us find other worlds around distant stars.
My collaborator, Paul Butler, and I dreamed up the idea of discovering planets around other stars back in the mid-1980s, before any planets were known.
What Butler and Marcy had realized is that the gravitational tugs that planets have on their stars would be revealed in the star's spectra in the form of Doppler shifts.
People indeed thought we were crazy to imagine that we could discover planets around other stars. If we could just detect the wobbles of stars precisely enough, then we could see the effects on those stars due to the planets. It wasn't good enough to just measure the Doppler shift of a star, and we had to measure the speed of a star to within about plus or minus 3 meters per second. If you think about 3 meters, that's about 3 good strides that you can walk. And that's eventually what we accomplished by the end of '95.
The simple act of letting sunlight pass through a prism reveals a lovely array of colors. This same process is what creates rainbows. Underneath that beauty lies some of the most fundamentally important processes in all of physics. The spectrum of colors does more than appeal to our aesthetic sense. It also tells us about the nature of our star, the sun. By breaking up the light from distant stars and clouds of gas, astronomers can determine their temperature, their density, their velocity, and even their composition, all without ever once coming in direct contact. A spectrum can yield all that information and more. It is a simple irony of nature that we can learn so much from so little. It is a further irony that we learn about some of the largest objects in our universe by studying the smallest. But each atom sends us a signal, a tiny pulse of light, and the study of that light reveals the nature of that atom, and the planet, star, gas, and even the galaxy in which it resides.